NASA has its official story, sure. But then there's the story the data tells, and sometimes those two just don't line up. When the gap gets big enough, people start poking around, asking questions nobody really wants to answer. The kind that make scientists shift in their seats. The kind that keep astronomers up at night, glaring at spreadsheets full of numbers that simply refuse to make sense. Questions like, what if we've been looking at 3I Atlas all wrong from the start? Picture this: a freezing night in November 2025. The sky is so clear you can see the Milky Way stretching overhead like someone spilled silver paint across the darkness. Somewhere in the US, a backyard astronomer lines up his telescope on a faint blur drifting through Virgo. The air barely moves. The only sound is the low buzz of his telescope, quietly fighting Earth's spin to keep that smudge centered. He's tracking 3I Atlas, the third known interstellar object, a true outsider just passing through on its way to nowhere. He's been on this thing for weeks, ever since the news broke. And he's not alone. There are thousands of amateurs out there, all hooked by the same idea. Something from outside our solar system, something that's spent who even knows how long drifting through starless dark before winding up here. He expects to see what everyone else sees, a fuzzy blob, maybe a hint of a tail if he gets lucky. Just the usual comet stuff, ice warming up, gassing off, leaving a streak of dust behind. But the photo he snaps that night, it shouldn't be possible, not with his gear, not at that distance, not if 3I Atlas is just what everyone claims. The official story is neat, clean, almost boring. 3I Atlas is a comet, nothing more. Just ice and rock from another star, melting and fizzing like every other comet when it gets close to the sun. NASA's press releases are careful, calm, and just technical enough to sound reassuring. It's just a cosmic snowball, they say. Nothing weird, nothing to see. Move along. But the real data, it's a mess. The readings from billion-dollar telescopes and observatories around the world, the deep-dive spectroscopic results, the weird polarimetric numbers, the orbital calculations. Put it all together, and you don't get a tidy picture. It's stranger than anyone's letting on, more tangled and, honestly, a little unnerving. Astronomers talk about it in hushed voices at conferences or trade late-night emails about the weirdness, but you won't see much about it in public reports. The real details get buried in technical appendices out of sight, because when you actually dig into what 3I Atlas is doing, when you look at those spectra, those polarimetric readings that don't match anything in the catalog, when you check its structure and realize it's holding together in ways comets just shouldn't, you start to notice things that don't belong. Oddities, contradictions, data points that huddle together in places where nature's not supposed to put them. Numbers that only make sense if you twist yourself into knots to explain them. And the more you stare at that data, the harder it gets to shake the feeling that we're looking at something new. Something that doesn't fit any of our old boxes, that pokes holes in everything we thought we knew about interstellar visitors. Something that quietly asks whether the universe is a lot more bizarre and a lot more crowded than we ever imagined. This isn't conspiracy talk. This is just what we're seeing, what the numbers and images actually show. Sometimes nature just refuses to play by our rules. When that happens, scientists hit a crossroads. They can admit the weird stuff is real, follow the evidence, and maybe risk their careers by saying things that don't fit the usual stories. Or they can smooth things over, highlight what looks normal, skip the baffling parts, and cross their fingers that nobody digs too deep. Honestly, the pressure to go with option 2 is overwhelming. Careers ride on being seen as experts. Funding hinges on showing you've got the established models down cold. Publish something wild without airtight proof, and you're basically asking to get sidelined. So when an object pops up that doesn't fit, say, something with features no other comet has, but that still lets off gas and grows a tail, well, the safe move is to jam it into the nearest familiar category and keep moving. But 3I Atlas changed the game. People are watching now, really watching. Amateur astronomers with gear that rivals the pros are snapping photos that catch details official telescopes somehow miss. Independent researchers are poring over public data and spotting patterns you won't find in the official write-ups. Online forums are buzzing with observations from every corner of the world, and people are noticing things that don't add up. The whole conversation has spilled out of the usual channels. It's messier, less controlled, but a lot more honest. And what people are finding, it's raising way bigger questions than just one weird comet. Like, how many of these things are slipping by us because we're looking for the wrong clues? Are our tidy little categories, comet, asteroid, whatever, actually up to the job, or are we missing a whole world of weirdness out there? And here's the big one. What if something artificial showed up but looked natural enough to fool us? Would we even notice? Nobody in an official role wants to tackle those questions head-on. To answer them honestly, they'd have to admit just how much we're still in the dark. So let's get real about 3I Atlas. Not the polished press release version, not the blurred images tweaked to fit expectations. Let's talk about what it actually looks like, through the eyes of people with nothing to lose. Let's talk about the hard data that makes seasoned astronomers stop mid-sentence. About the papers that bury their strangest results in the fine print, couched in language that almost, but not quite, says what they're really thinking. And here's something you notice when you talk to certain scientists, off the record when the microphones are off and nobody's watching. Ask about 3I Atlas and they'll pause, just for a split second before they answer. That hesitation, that's data too. It says plenty about the gulf between what they really think and what they're willing to say. Because in science, silence speaks louder than words. And when it comes to what 3I Atlas actually is, the silence is deafening. So how did we find it? On July 1st, 2025, the Asteroid Terrestrial Impact Last Alert System, ATLAS for short, picked up something odd moving through Virgo. ATLAS is a bunch of robotic telescopes run by the University of Hawaii, backed by NASA's Planetary Defense Coordination Office. Every 2 nights, it scans the whole visible sky, snapping images of millions of stars and checking for anything that moves or changes its brightness. That's when it caught 3I Atlas, and everything started to get interesting. That night in Chile, one of the Atlas telescopes picked up a faint blip, just this dim little dot that hadn't been there before. At first, it looked like nothing much. The automated system flagged it as another possible near-Earth object and pushed it along for follow-up, same as always. But when the folks at the Minor Planet Center got more data and crunched the numbers, everything flipped. The orbit made no sense. It zipped along too fast and cut across the solar system at an angle that didn't fit anything local. The more they tracked it, the clearer things got. This thing was on a hyperbolic path. It wasn't bound to the sun, wasn't swinging back around in a few thousand years. It was just passing through, a true interstellar visitor, making one quick loop before heading back out into the darkness between the stars. Only 2 other confirmed interstellar objects had ever shown up. First, there was 1I/Oumuamua in 2017, that weird cigar-shaped object that sped up as it left the sun. No obvious outgassing, just a bunch of wild theories. Maybe a light sail, maybe a lost probe, maybe something we couldn't even name yet. Then came 2I/Borisov in 2019, which actually acted like a textbook comet. Water vapor, carbon monoxide, the whole checklist. After that, most astronomers figured Oumuamua was just an oddball. Now there was 3I Atlas, and this time, everyone had a heads up. Instead of scrambling to study it as it sped away, they had months to get ready. The discovery came early, while it was still inbound, so there'd be a real chance to watch it up close at perihelion, the sun's closest approach, and then track it as it left. It was a rare shot to actually study an interstellar object in detail, maybe finally answer some of those big questions that Oumuamua left behind. And nobody wasted any time. News raced through astronomy circles within hours. Telescopes around the world started tracking it. Observing schedules got tossed out. Slots meant for galaxies and quasars were handed over. Scientists who'd usually be looking at local comets or planets dropped everything to focus on this new guest. Every big player joined in. Hubble swung around and caught crystal-clear images from above the atmosphere. The James Webb Space Telescope pointed its huge mirrors at the faint heat signature and started pulling out detailed spectra. Ground-based telescopes, from the Atacama Desert to Mauna Kea to the Canary Islands, pooled their data for a full view. Even spacecraft wanted in. Mars orbiters tweaked their routines to snap pictures as 3I Atlas passed by. Solar probes like Stereoway and SOHO, which usually just watched the sun, caught it drifting through their sights. It was all hands on deck, an international, multi-wavelength effort that only happens when something truly rare pops up. Timing made all the difference. Because they spotted 3I Atlas while it was still far out and inbound, scientists got to watch it slowly wake up, see it go from a frozen, silent hunk to an active comet, shedding gas and dust as the sun warmed it up. They could study its untouched interstellar surface before sunlight changed it. Every tool astronomers had, spectroscopy, polarimetry, photometry, you name it, got thrown at this thing. It was a once-in-a-lifetime shot, and nobody wanted to miss a single detail. That was the plan anyway. Everyone expected a simple, clean mission. Fly out, study this interstellar comet, figure out what it's made of, learn a little about how it formed, maybe get a glimpse into how other solar systems work. The usual. Take the data, write the papers. If the results were good, maybe even snag a Nature publication. But that's not what happened. Instead, the comet threw curveball after curveball. It just wouldn't fit into any of the tidy boxes scientists like to use. Every time they thought they understood it, the numbers said otherwise. The closer they looked, the weirder it got. Perihelion, the closest point to the sun, rolled around on October 30th, 2025. The comet swung into about 1.4 astronomical units from the sun. For reference, 1 astronomical unit is the distance from Earth to the sun, roughly 93 million miles. So 3I Atlas was closer than Mars, but still nowhere near Earth. It was close enough that the sun's heat should have started cooking the comet, making it shed gas and dust, but not close enough to show up as a bright spot in the night sky. For a typical comet, perihelion is showtime. All those frozen ices, water, carbon dioxide, carbon monoxide, finally get enough sunlight to jump straight from solid to gas. No melting, just instant vapor. That's what creates the coma, the big glowing cloud around the comet's center, and the tail that streams away from the sun. It's dramatic stuff. And sure, 3I Atlas put on a little show. It grew a coma. It started releasing gas and dust. Instruments picked up the outgassing just as the textbooks predict. On the surface, it looked like a comet doing comet things. But here where it got strange, the details were all wrong. The way the coma formed, the mix of gases, how everything evolved over time, none of it lined up with what's normal. Not even close. And the differences weren't the kind you can just chalk up to bad data or a weird fluke. The first real shock came from the spectroscopy. That's when you split up the light from the comet and look for signatures of different chemicals. Each gas leaves its own unique mark, like a cosmic barcode. Scientists pointed their spectrographs at 3I Atlas expecting to see water, because honestly, that's what you always see. Water ice dominates comets. It's not even close. Usually, it's 70 to 90% of the ices. When that water vaporizes, you get a strong signal, plus all sorts of related molecules like hydroxyl radicals. There's usually some carbon monoxide, some carbon dioxide, maybe traces of methane or ammonia, and a dash of organic stuff. But water always leads the pack. That's the whole dirty snowball image emphasis on the snow. But this time, 3I Atlas flipped the script. The James Webb Space Telescope tuned in, using its infrared spectrographs to get a really sensitive look at the gases. And what did it find? Carbon dioxide, not water, was running the show. The CO2 to H2O ratio wasn't just high, it was off the charts. Some estimates said there was 10 times more carbon dioxide than water. For any comet in any solar system, that's unheard of. That's not just unusual, it's wild. We're looking at a comet with a chemical makeup so far off the charts, you can't even compare it to the regulars in our solar system. You need a whole new formation story to make sense of it. The mix of water and carbon dioxide in a comet's ice isn't random. It all comes down to the temperature and chemistry in the protoplanetary disk where it formed. Water ice isn't that picky. It forms and sticks around in places colder than about 150 Kelvin, which, in cosmic terms, isn't all that frigid. Carbon dioxide ice, on the other hand, needs a real deep freeze, below about 70 Kelvin. Back when our solar system was just getting started, you had this temperature gradient in the disk. Water ice dominated the outer planet region, but carbon dioxide, it was scarce. A few oddballs out past Neptune or in the scattered disk picked up more carbon dioxide, but water always led the pack. Now, 3I Atlas flips that script. It's got so much carbon dioxide compared to water that it almost certainly formed somewhere much colder than our solar system's backyard, maybe way out in the far reaches of a protoplanetary disk around some cooler star, or in a place where carbon and oxygen played by completely different rules. This is chemistry waving a big red flag saying, "I'm not from around here. I grew up under conditions nobody's ever directly seen." That kind of signature is gold for science. It tells us there's way more variety in how planetary systems form than we've ever seen up close. And honestly, it's a little unsettling. This isn't just a visitor from another star. It's got a composition that feels downright alien. Every time we measure something, we learn about chemistry that happened in a place we'll never see, around a star we might never even find, under conditions we're only guessing at. When something is that strange in one way, you start to wonder, what else could be off about it? What other surprises are hiding under the surface? How many of our assumptions just don't hold up? Then there's the whole issue with its size, and this is where things really went sideways. Figuring out a comet's diameter sounds easy, but it's actually a mess. You're trying to measure a solid core that's hidden deep inside a glowing ball of gas and dust. You never really see the nucleus directly. It's all mixed up with sunlight bouncing off the surface and scattering through the coma. To untangle all that, you have to make a bunch of guesses. How shiny is the surface? What astronomers call the albedo? How much dust versus gas is getting kicked out? What's the angle between the sun, the comet, and us? How thick is the coma? Every answer depends on which assumptions you feed into the model. For 3I Atlas, these guesses spat out results all over the place. Depending on which model and which observations you trusted, the nucleus could be anywhere from 440 meters to 5.6 kilometers across. That's not just a little margin of error. That's a full order of magnitude, from something the size of a city block to a small mountain. Put it in Earth terms, 3I Atlas could be as small as the Empire State Building is tall, or as wide as a major city. On the small side, you could fit a bunch of these nuclei in Central Park. On the big side, you're talking about something as big as Manhattan below Central Park. Why are the estimates all over the place? Honestly, it's because different research teams made different guesses and landed in totally different places. Nobody could say whose assumptions were actually right. The one thing everyone agreed on was the brightness we saw, the total light coming from the object. That was real, measured data, but figuring out the size of the nucleus from that brightness, that's where things went sideways because every group used a different model and none of them lined up. Let's say you think the surface is very dark, almost like charcoal. That would mean most sunlight gets absorbed, so the nucleus would have to be big to explain all the brightness we see. But if you figure the surface is brighter, more like dirty ice, you don't need such a big nucleus. It could be much smaller and still reflect enough light. Then there's the dust in the coma. If you think most of the light comes from that dust, you end up with a smaller nucleus. If you figure it's mostly the nucleus reflecting light, you get a bigger one. So, your answer depends on which assumptions you buy into. And this isn't just a technical detail. The size matters way more than you'd think. A comet's activity, how much gas and dust it spits out, depends on both its surface area and how much sunlight it's soaking up. If the nucleus is small, say around 440 meters across, that's not a lot of surface to work with. To get as much outgassing as we see from such a tiny area, the ice would have to be going wild, way more active per square meter than any comet we've seen. You'd need the surface to be roasting hot, way hotter than solar heating alone predicts, or you'd need some buried heat source, Or maybe the ice is something super volatile that evaporates at low temperatures. None of those ideas are impossible, but everyone calls for something extra, something unusual about this particular object. You have to start making extra assumptions, and each one piles more uncertainty on top of the already shaky size estimate. But suppose instead the nucleus is big, more like 5 or 6 kilometers across. Now the surface area is much larger, so you don't need such crazy sublimation rates to explain the observed activity. The math works out better, but then you hit a new snag. Why does such a big object look so faint? Why hasn't it held together better, since bigger comets have more gravity to keep them from breaking apart? Large comets usually act differently than small ones because they're tougher to shatter. They should be brighter too, unless their surface is really dark. So if it's big, you have to explain why it's so dim, why it absorbs so much light instead of reflecting it. That's another oddity. So neither the small nor the large nucleus explanation fits perfectly with everything we see. Both force you to reach for special explanations. And with this much ambiguity, when you can't even nail down the size, other, weirder ideas start to look tempting. Because when all your models give wildly different answers, people start to wonder if the models themselves just don't fit. What if 3I Atlas isn't shaped like a typical comet at all? Maybe it's not a messy ball of ice and rock. Maybe its structure is so different that all our usual size guessing tricks, which work fine for solar system comets, just don't apply. Maybe we're looking at something that doesn't play by the usual rules, a comet nucleus, but not as we know it. No one has real answers yet, but just the fact that people are even asking these questions, sometimes just passing comments in the hallway, shows how much this object has messed with our expectations right from the start. And honestly, the weird composition and the strange, uncertain size, that was just the warm-up act. Things really got interesting when the polarimetric data started rolling in. Suddenly, you had seasoned astronomers leaning over to each other after conferences, talking in hushed, careful voices, picking their words so precisely you could tell they were unsettled by what they were seeing. Polarimetry sounds like one of those complicated niche astronomy tools, but it's quietly powerful. When light bounces off stuff, rocks, dust, whatever, the photons get their act together. They start lining up, moving in step instead of just vibrating every which way. If you measure which direction the light's polarized and by how much, you can figure out all sorts of things. What the surface is like, how big the dust grains are, what they're made of, even how everything's arranged. It's like a secret code built into the light, just waiting for the right instrument to crack it. Astronomers have leaned on polarimetry for ages to learn about comets and asteroids. They know the patterns. There's a playbook. Measure polarization versus phase angle. That's the angle between the sun, the object, and you always see these familiar curves. At small phase angles, when the sun is almost right behind you, the polarization goes a little negative. The electric fields line up perpendicular to the scattering plane, but with the opposite sign compared to larger angles. As you move to bigger phase angles, the polarization flips from negative to positive, climbing to a peak, then dropping again at the biggest angles. This curve is like an ID badge for solar system objects. Deviations are rare, and when they show up, they matter. The exact dip, the crossing point, the curve's shape, all of it ties directly to things like particle size, surface roughness, and composition. These curves are diagnostic tools, giving you a peek at stuff you just can't measure any other way. But then came 3I Atlas, and it didn't even come close to following the script. A careful polarimetric study before perihelion, multiple observatories, different wavelengths, all the right protocols, found something no one had ever seen. The negative polarization branch, that signature dip at small phase angles, was way deeper and way narrower than anything measured from any comet or asteroid. We're talking minus 2.7% polarization at those small angles, with the zero crossing happening around 17 degrees. Those numbers probably sound like gibberish unless you're deep into polarimetry, but to the experts, it was a genuine jaw-drop moment. Somehow, the way light was bouncing off 3I Atlas, whether it was the nucleus, dust in the coma, or some mix, just didn't match up with any known object. Not any comet, not any asteroid. Nothing in all the decades of cataloged observations. The polarimetric signature was truly one of a kind. It didn't fit anywhere. So what's behind that? What physical scenario could create such a wild result? The research papers started floating theories, each one careful, every sentence loaded with caveats. Maybe the coma dust grains were tiny, way smaller than typical comet dust, scattering light in totally new ways. Or maybe the grains themselves had bizarre, complicated shapes, like little fractal tangles, twisting the light in ways we haven't seen before. Maybe the composition was just weird, materials with optical properties you don't see in any comet around here. Or maybe something happened to the surface, something that changed how it scatters light in a way nobody's observed before. Then again, and this only ever came up in roundabout ways, never head-on, maybe there's some kind of structure to the scattering regions. Not just random patches, but an actual pattern, some geometry we don't have the right models for. You can read a lot between the lines in these papers. When scientists know what's going on, they just say it. They're clear, even bold. When they don't know, they admit it and spell out what data would help. But sometimes you can tell they sense something but aren't ready to put it on paper. That's when the writing gets cagey, passive voice, hedging, hints instead of statements, implications dangling for the reader to piece together. The polarimetric studies on 3I Atlas are packed with this kind of careful writing. You get lines like, the observed scattering properties suggest surface characteristics unlike those of typical solar system comets. Or, further investigation is needed to understand the unusual polarimetric behavior. Sure, that's all technically true, and it's appropriately cautious. But it feels like nobody wants to stick their neck out and actually say what they're thinking, even though the measurements are so detailed you'd expect them to point somewhere specific. One researcher just came out and said it, off the record, at a conference. We've measured the polarization of hundreds of comets and asteroids. We know what causes different signals. This doesn't match anything. If you handed me this data without context, I think something went wrong with the instruments or the data processing. But the measurements hold up. Different teams, different telescopes checked and rechecked. It's real. It just doesn't make sense with anything we know. That's not proof of something wild or artificial. Nobody saying that. But it's a clear sign something about this object just doesn't fit and nobody has a good natural explanation. The data is solid. The observations are careful. The meaning is still out of reach. And when the meaning stays out of reach for this long, when group after group looks at the same numbers and can't agree on what could cause them, that's when the stranger ideas start to look less ridiculous. At some point, you start to wonder, what if the basic assumptions are off? What if this thing really is different in ways we haven't even thought about? What if our neat categories, comet, asteroid, natural, artificial, just don't work for this case? Nobody asks those questions in the published papers, but behind the scenes they come up. And the more strange data arrives, the more those questions get asked. While astronomers were quietly wrestling with the odd polarimetry data, another set of observations started to stir up its own batch of questions. All over the world, telescopes, some tucked away in professional observatories, others set up by dedicated amateurs in their backyards, followed 3I Atlas, trying to track the shape and behavior of its coma and tail. When scientists talk about morphology, they mean the actual structure, how the gas and dust spread out around the comet, how those patterns change with time, the whole messy dance. Usually when you look at comets up close, they're a mess. The coma isn't this smooth glow, it's patchy, full of structure. You see jets, narrow streams of material blasting out from active spots where ice is doing its best to turn straight into gas. As the nucleus spins, different parts get sunlight, so the jets start, stop, and shift, making the whole thing flicker and pulse. The tail's got its own drama too, with streaks and filaments bent and twisted by the solar wind. That's just how comets are. Their nuclei are lumpy, random chunks of ice and rock with volatile stuff stuffed in wherever it landed. Sunlight hits one side more than the other, and as the comet rotates, new spots wake up while others cool down. The result? chaos. Gorgeous, complicated chaos that photographers love and scientists obsess over, because every detail tells you something about the comet's spin, its makeup, or where its ices are hiding. But 3I Atlas wasn't playing by those rules. Most nights its coma looked way too symmetrical. Not perfectly so, nothing in space ever is, but way smoother and more uniform than you'd expect. The big dramatic jets you see in most comets. Gone or so faint that even experienced observers couldn't agree if they were real. Some people thought they spotted hints of jets, but even then they called them subtle and tough to confirm. Others just saw a soft, even glow, and when any structure did pop up it wouldn't behave. The features seemed to show up and vanish or twist around in ways that didn't match any obvious rotation pattern. If there was a system, nobody could figure it out. The tail just made things weirder. Instead of a classic single tail streaming neatly away from the sun, teams kept reporting oddities. Parts of the tail that brightened or faded for no clear reason, features sticking out at strange angles, even anti-tails, features that, weirdly, pointed toward the sun instead of away from it. Anti-tails aren't impossible. Geometry can play tricks on you when you see the comet's dust plane edge-on. But 3I Atlas seemed to pull this trick more often and more dramatically than other comets. And beneath all this, there was a deeper mystery. 3I Atlas refused to settle down. Even far from the sun, where most comets go quiet or barely sputter, it was still furiously outgassing. Space telescopes watching in ultraviolet picked up clear signals of hydroxyl, a dead giveaway that water molecules were breaking apart, at distances past 3 astronomical units. That's way beyond the water-ice frost line, the point where sunlight is too weak to keep vaporizing water ice. Out there, the sunlight drops to about 11% of what Earth gets. Surface temperatures on a comet at 3 AU, maybe 130, 140 Kelvin. That's too cold for water to sublimate in any big way. So why was 3I Atlas still venting water? For that to happen, you'd need something special. Maybe the ice is incredibly pure, not buried under the usual crust of dust and organics that insulates most comets. Or maybe the surface is pitch black, soaking up every sliver of sunlight and turning it straight into heat. Or there are hidden reservoirs under the surface, with cracks letting the gas escape. Or, and this is a wild card, there's some kind of internal heat source, something besides just the sun. Sure, any of these could happen. Physics doesn't rule them out. But they all raise the same nagging question. Why this comet? What makes 3I Atlas different? The energy puzzle just kept getting harder to ignore. If the nucleus is small, and the outgassing is really as intense as the numbers suggest, where's all that energy coming from? The paper that reported these results played it safe. The conclusion said, the thermal model may require refinement to account for the unusual properties of this interstellar object, and further observations and laboratory studies of exotic ice compositions may help resolve the discrepancy. Basically, our models aren't working and we don't know why, but that's not some big scandal. That's just how science works. Models break all the time, and when they do, they show us where our understanding falls short. That's how progress happens. Still, when different teams working separately all run into the same problems, when everyone starts reaching for special explanations just to make the numbers fit, you start to wonder. Maybe we're all leaning on some basic assumption that just isn't right. No single observation by itself proved anything wild was going on. Weird composition. Sure, interstellar objects form in other places, so weird isn't unexpected. Unclear size. The measurements are tough and the data is sparse, no surprise there. Odd polarimetry, scattering physics is tricky. Maybe our models just aren't up to the task. Strange shape. Every comet's got its quirks. Too much activity far from the sun. Maybe it's just got unusual ices or super volatile stuff locked inside. Every odd result had an explanation you could live with. But when you looked at them all together, the story got harder and harder to sell as just another interstellar comet. Every new bit of data felt like another piece that didn't quite fit the puzzle. And scientists, for all the stereotypes about being robotic or detached, are people. When the answers don't add up, when the data won't play nice, it gets under your skin. You get frustrated. You start to wonder, sometimes quietly, sometimes not, if something bigger's going on. And then came the photo that changed everything. The shot that yanked this whole story out of the technical weeds and into the spotlight. The image that made it impossible to write off 3I Atlas as just another slightly oddball comet. The photographer wasn't some tenured astronomer or research fellow. Paul Craigs isn't a familiar name in the pages of the Astrophysical Journal. He doesn't have a PhD, doesn't work at a fancy observatory. He's an astrophotographer, one of those people who do this because they love it, not because they want a grant or a citation. He's got a regular day job. At night, when the skies are clear, he heads out to his backyard observatory somewhere in the US, a little dome with a consumer telescope and camera setup. His gear is solid, the kind of thing serious hobbyists buy after years of practice. A Dwarf 3 telescope, small, portable, automated, made for astropics. Not what you'd find in a professional observatory, but good enough that, in the right hands, it can pull out some pretty amazing shots of galaxies, comets, planets, whatever's out there. It's the kind of setup that sits right between backyard stargazing and the pros. So, on November 15, 2025, with the air cold and the sky clear, Craigs aimed his telescope at the spot where 3I Atlas was supposed to be. He'd been following this thing off and on since the first news broke, just like thousands of other amateurs around the world. Another visitor from another star, who wouldn't be curious. He'd seen it before, too, just a faint blur, nothing much unless you really worked at teasing out the details. Tonight, he wanted more than just another routine observation. The object had moved closer, shining brighter now, and showing a kind of restless energy as it kept cruising away from the sun. The moon was gone, the sky was deep and dark, almost perfect. He set up his imaging run, a series of exposures at different wavelengths, each one precisely timed to catch the comet as it slid past the background stars. The telescope handled the tracking on its own, compensating for Earth's slow spin, always keeping the comet right in the center. The camera quietly gathered photons, one after another, slowly building up the signal. When the session wrapped up, Craigs downloaded the images and got to work. This was the usual astrophotography grind, stacking frames to smooth out the noise, calibrating to clear away quirks from the hardware, stretching the histogram to tease out faint details, sharpening to pull out structure, adjusting colors to highlight what the comet was made of. Standard stuff. Nothing wild. It's what the pros do and what serious hobbyists know by heart. But as the final image came together, Craig saw something he absolutely didn't expect. Right there in the middle, a bright, almost blinding white core, crisp and sharply outlined, nothing like the smeared blobs he'd seen before. The nucleus, if that's really what it was, stood out, looking both smooth and clean-edged. The way the light fell off just didn't feel natural. And around that core, a faint blue glow unmistakable. It wasn't the dusty brown or yellow tint you normally see from sunlight bouncing off comet dust. Not the reddish tones that show up when organic stuff gets involved. This was blue. A clear, luminous blue that seemed to wrap the core, not like reflected sunlight, but like the thing itself was shining, glowing from within. Honestly, the whole thing felt off. Not at all like the messy, lopsided comets in textbooks. Nothing like the official Hubble shots of 3I Atlas, which show a blurry ball with a fuzzy, uneven coma. This was different, clean, geometric, organized. And well, there's just no way around it. It looked deliberate, engineered, artificial. He stared at the screen, trying to convince himself he'd messed up somewhere. Maybe he'd gone too far with the sharpening. Maybe the stacking process had introduced weird artifacts. So he started over from scratch. Tried different parameters, different techniques, but the core stayed sharp and the blue glow didn't disappear. This was the data. The telescope had really seen it. Craigs decided to share what he'd found. He posted the image on astronomy forums alongside all the technical details. What gear he used, exposure times, how many frames, exactly what steps he'd followed. He wasn't making any wild claims. He wasn't saying, "Look, aliens." He just wanted people to look and tell him what they thought. It didn't take long for the image to blow up, not just in amateur astronomy circles, but all over social media, Reddit, YouTube, Twitter. The reactions came fast. Some accused him of overprocessing, said he'd wrecked the data with too much sharpening, or used bad techniques that faked the details. Others were sure it had to be a hoax, that someone had just dropped a spaceship into a comet photo using Photoshop. But then something changed. Other amateurs started chiming in. Different telescopes, different cameras, different places on Earth, and their images showed the same strange features. Not exactly the same, since everyone's angle, gear, and weather were a little different, but close enough. Close enough that you couldn't just write it off as a fluke or a trick. The pattern was there, and people started to notice. Down in Australia, someone with a different telescope and some other software caught a central bright spot, really sharp, almost too sharp. Over in Europe, another astronomer snapped a picture and saw something weird, a blue glow that didn't match the usual dust you'd expect from a comet. Meanwhile, in South America, someone uploaded photos showing the inner coma with these clean geometric shapes. None of them knew about the others. Nobody planned this. Yet they were all picking up on the same odd thing. The pattern kept repeating, a bright, crisp core more defined than you'd expect. A glow, usually blue or blue-white, that just didn't look like normal comet dust. The whole thing looked way too organized, too neat, too structured for a comet. Comets are supposed to be messy, breaking apart, unpredictable. Mainstream science didn't waste any time. NASA's public affairs folks put out a statement. 3I Atlas is a comet, end of story. They blamed the weird images on amateur mistakes, artifact from image processing, observer bias, small telescopes not up to the job. The pros, they said, see a regular comet. Hubble's photos, fuzzy core, messy coma, exactly what you'd expect. Nothing strange, move along. But for people actually paying attention, that answer just made things more confusing. If pros see a comet, why do amateurs keep seeing something else? If it's just artifacts, why do people all over the world, using different gear and different methods, end up with such similar results? And honestly, if amateur images are so flawed, why do they show details that Hubble seems to wash out? Some professional astronomers tried to explain. Amateurs, they said, get raw, unfiltered data, no fancy correction or calibration. Hubble and JWST, on the other hand, run everything through layers of processing, stripping out instrument quirks, fixing distortions, subtracting backgrounds, all to get numbers you can trust. That's what good science needs. But those pipelines also smooth out real features, especially if they don't fit the normal model or they're right at the edge of what the telescope can resolve. The software assumes it knows what a comet should look like. If this thing breaks those rules, the processing might erase real stuff by accident. Amateurs, with their simpler setups and less polished software, just point, shoot, and try to capture the detail. They're not after perfect scientific data, they want the image to pop. Sometimes that's an advantage. The lack of heavy processing means they might catch things the pros accidentally scrub away. But there's another idea, one the pros don't say out loud, but the amateurs talk about more and more. What if Hubble's images look normal because the software makes them normal? Those calibration steps, based on years of seeing regular comets, might be forcing this object to fit the usual mold. What if the amateurs are actually catching what's really there, because they're not following the rules about what should be there? That's a tough thing to prove. You'd have to dig into the raw, untouched Hubble data and redo everything from scratch, ignoring the usual assumptions. You'd need to check if the features from amateur photos are truly missing in the pro data, or if the processing just covers them up. Doing that takes time, technical know-how, and access to archives most people never see. The question wouldn't just disappear. People kept circling back, and before long, the debate about these images turned into something bigger, something about how we know what we know. How much do our own expectations color what we see? And when you've spent years building expertise, does all that knowledge start to filter out the things that don't fit? Professional astronomers can't help but see 3I Atlas through thick layers of theory and habit. They've spent decades with comets. They also feel the pressure to steer clear of wild claims that might blow up in their faces. Amateurs, on the other hand, don't carry that weight. They see things fresh, less baggage, nothing much on the line. Sometimes the experts catch details the rest of us miss. Other times, it's the newcomers who spot the truth the veterans have trained themselves to overlook. What really made this whole thing messy wasn't just the technical squabbling over images. It got weird when people started poking through the actual published papers, not the flashy press releases or the watered-down summaries, but the real deal in Nature Science, the astrophysical journal Icarus. These papers had survived peer review. They were supposed to be the gold standard, careful, rigorous, done by the pros. But when you read those papers, something felt off. Not that anyone was lying or fudging data. The strangeness was more subtle. It was like the authors themselves didn't trust their own results. You could feel the hesitation in every paragraph. The language was cautious, more than usual. Conclusions got wrapped in so many qualifiers and hedges, you started to wonder what wasn't being said. Sometimes the implications just hung there, unspoken, as if the writers were sidestepping ideas that seemed too out there, even when the data nudged in that direction. Take the polarimetry paper, the one with that bizarre negative polarization branch. The authors lay out their data, error bars, methods, the works. They compare 3I Atlas to everything in the solar system. Nothing matches. Then in the discussion, they start tossing out possible explanations. Maybe it's tiny particles, weird shapes, strange chemistry. Every single point gets softened. May indicate, could suggest, possibly consistent with. They hedge everything. That's fine up to a point. Scientists should be careful when they don't have much to go on. But there's a line between healthy caution and outright reluctance. And honestly, reading between the lines, it feels like the authors are only offering these explanations because they have to, because peer review expects some kind of answer. Deep down, they don't seem convinced. It's like they're just ticking the boxes, writing out the most reasonable-sounding ideas, while quietly signaling that none of it really adds up. Or look at the spectroscopic studies, the ones that found crazy high levels of carbon dioxide compared to water. Multiple teams, different instruments, same basic result. CO2 completely outstrips H2O in a way nobody's seen before. The data is solid, but when it comes time to explain it, the answers get hand-wavy. 3I Atlas must have formed in a different kind of system with different chemistry. Well, sure, that's what interstellar means. But what does different chemistry actually mean here? What kind of protoplanetary disk? What temperature? What kind of star? You barely get a hint. The papers just wave at poorly constrained formation models or uncertain chemical evolution in exoplanetary systems, which is a nicer way of saying, honestly, nobody knows. And the models aren't any help. The papers about size uncertainty actually say more in their silences than in their words. The possible diameters swing wildly over a tenfold range. Change a few assumptions and you get completely different answers. And yet, nobody in the main text ever just asks the obvious. Why can't we figure this out? With Hubble, JWST, and all those ground-based telescopes, how are we still so clueless about something as basic as size? You have to dig through technical appendices and the fine print to find the real answer. It's pretty simple. The object isn't acting like we expect, and our models just don't work here. The brightness we see can't be split up neatly into this much reflected from the nucleus, that much scattered by dust, because the coma isn't playing along. The usual formulas, brightness, size, albedo, dust production, they just fall apart. So we end up with a huge mess of uncertainty, and no good way out unless we get data that, honestly, we just don't have. But here's what's really interesting. Not one peer-reviewed paper ever brings up the possibility that 3I Atlas is something unnatural. Nobody says, hey, maybe it's artificial. No one even hints that design could be behind these oddities. It's a total blank spot in the official record. And that silence stands out because behind closed doors, in hallway chats at conferences, in emails, scientists are obviously thinking about it. You can hear it in the way they talk, the guarded language, the little hesitations before they answer. They never say it straight out, but you can tell it's there. One veteran researcher, someone who spent decades picking apart comets and asteroids, spoke off the record at a conference. This is someone who knows the business backward and forward. When asked about 3I Atlas, they basically said, if you handed me this data with no context, no name, no discovery location, and asked what it was, I wouldn't say comet, I'd say unknown. I'd want a lot more data before I guessed. The composition's odd. The polarimetry doesn't fit anything familiar. The structure's too stable. The activity's off. You could probably explain each weird bit with some one-off scenario, but when you stack them all up, it just bothers me. It doesn't feel right. Then they paused. But I can't put that in a paper, can I? It doesn't feel right isn't science, and suggesting it's not natural, unless you have ironclad proof, that's a good way to end your career. So we write cautious papers, unusual object, more study needed, and move on. That's not some sinister cover-up. It's just scientists dealing with real pressures. The whole extraordinary claims need extraordinary evidence. Thing sounds fair, but in practice, it's a trap. You can't seriously propose a non-natural explanation without proof, but you also can't gather proof if even suggesting that hypothesis brands you as a crank. So everything grinds to a halt. The right questions don't get asked. The anomalies get smoothed over. The careful language in the actual research gets lost when the press releases come out, which just trumpet comet from another star and leave out all the caveats. The awkward questions get dropped from public statements. Scientists who are genuinely uneasy about the data keep their worries behind closed doors, only talking about them with trusted colleagues, never on the record. But honestly, that kind of silence doesn't work anymore. Not now, when thousands of amateur astronomers have their own telescopes, their own software, their own ways of sharing what they find. You can't put the lid back on when uncomfortable images are flying around social media, seen by millions before anyone official even notices. Paul Craig's posted his image, and within a day, hundreds of thousands of people had seen it. Other observers started digging through their own data, reprocessing images, and finding the same weird features. The conversation jumped the fence, no longer locked in the ivory tower. It got messier, more chaotic, more open. But in a way, it got a lot more honest, too. People without professional reputations on the line or grant funding tied to staying in the good graces of institutions. They get to ask the questions professional scientists can't risk voicing out loud. They can point out what everyone's quietly thinking. Sometimes the official story doesn't add up. Sometimes the emperor really doesn't have any clothes. Something genuinely odd happens, and pretending it's all perfectly normal just feels dishonest. Take 3I Atlas. The official line calls it a comet, an oddball from another star system, sure, but still a natural object following the laws we know. But when you actually dig into the data, it doesn't fit. It acts nothing like any known comet. It breaks the rules. Even the researchers, the ones who have stared at the data for months, end up uncomfortable, though most of them won't say that out loud. Their silence says enough. They've tried to make the models fit, tried to explain it away, but nothing works unless they start making up special rules at every turn. And that's silence. It's not just confusion, it's fear of what it means if the official story is wrong. Because if 3I Atlas isn't really a comet, or at least not the kind we've always pictured, then everything gets shaky. Suddenly you have to wonder if we got Oumuamua wrong too, or if there are other weird interstellar objects flying by that we've missed completely. Just because we're looking for the wrong things, expecting the wrong behavior. We might have to admit the galaxy is messier, busier, and a whole lot weirder than we've let ourselves believe. Maybe space isn't just empty but full of stray objects, natural, artificial, or something in between, drifting between stars, showing us patterns we never thought to look for. That's a scary idea, not because we're on the edge of disaster, but because it means we're profoundly in the dark. Maybe we've been trying to shove the universe into neat little boxes, categories that don't really fit. Maybe reality doesn't care about the rules we've written down. And if first contact ever happens, or already has, it probably won't look like the movies. No blinking radio signals, no fleets of alien ships. It might just be ambiguous stuff, objects sitting right at that uncomfortable edge between natural and artificial, acting normal enough to be ignored, but strange enough to make you wonder. The worst part is the not knowing. If 3I Atlas was obviously artificial, sending out signals, doing impossible maneuvers, We'd know what we were looking at. We could react. But it's not. It's stuck in this gray area where nothing quite rules out the ordinary explanation, but nothing fits it either. Ambiguity is exhausting. Certainty, even if it's terrifying, at least lets you act. Ambiguity just leaves you stuck, unable to believe, unable to dismiss, suspended between possibilities. So science, as an institution, does what it always does. It plays it safe. It sticks to what can be measured and published without ruffling feathers. The papers come out, careful and precise, making observations but steering clear of anything too wild. Everyone waits for more data, knowing that 3i Atlas is slipping away, getting dimmer, and the chance to get real answers is closing fast. They're hoping quietly that the next interstellar visitor will show up with fewer question marks. Something clear, less unsettling, less likely to make everyone wonder if our whole idea of normal in the universe is just wrong. But just hopping doesn't get you answers, and staying quiet doesn't either. The data's out there. The weird stuff is real. It's in the peer-reviewed papers, right there for anyone willing to look past all the cautious phrasing and actually check the numbers. These aren't just wild guesses. The questions are legit, grounded in real measurements. And the longer nobody addresses them, the more people spin up their own theories, some reasonable, some totally off the wall, all of it feeding that nagging sense that something important is being kept under wraps by the experts who should be telling us straight. What 3i Atlas actually looks like depends a lot on who's looking and what they expect to see. The official telescope images, run through software built for normal comets, just show a fuzzy blob with an awkward halo. But amateur astronomers, using different tools and fewer assumptions, pick up details that seem stranger, more structured. The spectroscopic data. It points to a chemistry we've never seen in our solar system. Polarimetry shows optical properties that don't match anything we know. And the orbit. There are little nudges in its path that suspiciously line up with what you'd expect if something was actively steering. If you dig into the published articles, you see scientists dancing around conclusions they can't quite say out loud. They note the oddities, but then rush to explain them with theories they don't really buy. All of that is written down. All of it is real. The question is, what does it mean? And right now, as 3i Atlas drifts out of the solar system, late 2025, no one really knows. Or maybe someone does, but they're definitely not saying it in public. So we're left with a mystery, not the fun, Sherlock Holmes will figure it out kind. It's the uncomfortable, open-ended type, where you're not even sure there's an answer, or if the answer would even make sense to us. It's a mess of observations that refuse to fit neatly into any box, that demand our attention but won't give us a clear story. Maybe we'll get more data. Maybe someone will build a model that explains it all, exotic ice, weird light scattering, you name it, and suddenly it'll all seem obvious in hindsight. Maybe the processed interstellar traveler idea will hold up, and we'll realize cosmic rays just do strange things to these objects over millions of years. Maybe 3i Atlas becomes the poster child for a whole new category of stuff that spends eons drifting between stars. Or maybe we'll never know. Maybe it'll slip away before we can pin anything down. Maybe it'll join Oumuamua in that uneasy group of visitors, too weird to ignore, too ambiguous to force a real answer. They almost make us question everything, but not quite enough to break through our doubt. And maybe that's the real lesson. Not that 3i Atlas is for sure artificial, but that we might not even notice if it was. Our methods for telling the difference between natural and artificial, maybe they're not as solid as we think. Something could cruise right past us, acting strange enough to make the experts uneasy, and we'd still fall back on natural explanations, mostly because the alternative is just too hard to prove and way too risky to say out loud without proof. That silence says a lot. When comet scientists, the people who have spent decades with this stuff, look at 3i Atlas and hesitate before giving it a label, that pause means something. When the weirdest findings get tucked away in appendices or supplementary sections of papers, that tells you what's okay to say in the open and what is. When amateurs snap photos that show features official instruments miss or smooth away, that's a clue, too. Maybe our whole system for looking at these things is biased, quietly nudging us to see what we expect instead of what's really there. The universe doesn't owe us anything, not clarity, not comfort, not tidy answers. It just is, whether or not we find its workings satisfying or even comprehensible. Sometimes the most honest thing you can say in the face of a cosmic mystery is that you do know. The data's weird. The questions are real. Pretending otherwise doesn't help anyone. Take 3I Atlas. We know it came from another star. That much is solid. It shot through our solar system on a hyperbolic path, way too fast to be caught by the sun, and now it's heading back out into interstellar space. We threw everything we had at it: space telescopes, adaptive optics, spectrographs, hunting for faint chemical clues, and what we got back was just strange. The readings were off the charts. The composition was more extreme than we expected. The way it scattered light, never seen anything like it. Its shape stayed weirdly stable, too smooth. Its activity didn't drop off when it should have. Even after months of tracking, we couldn't pin down its size. Every new observation just added to the pile of things that didn't add up. That's what really happened. The rest, interpretations, theories, models, that's us, doing our best to find patterns in the noise. Those explanations always carry some uncertainty. They reveal our assumptions as much as they reveal the truth. Even the smartest experts get it wrong sometimes, no matter how well-intentioned or qualified. So what do you do with all that uncertainty? You sit with it. You admit it's there. You resist the urge to force a neat answer just because the ambiguity feels uncomfortable. You keep looking, keep measuring, keep asking new questions, even if the answers seem to slip further away. Some mysteries just won't budge, not in a year, not in a lifetime, maybe never, and you keep watching the sky. 3I Atlas won't be the last of its kind. More interstellar visitors will show up, because that's what the galaxy does. It's chaotic and full of debris, with objects getting booted from their home systems and wandering for millions of years. Some will drift through our patch of space by pure chance, following paths set by gravitational runs we'll never fully retrace. Some might even be on purpose, though proving that is almost impossible. Each one that passes by is a message from somewhere else. A sliver of information about how planets form in other solar systems, about what happens in places we can't reach. Every visitor is a chance to learn something we'd never figure out otherwise, because we can't go to the stars yet. All we can do is wait for a piece of them to come to us. The big question is, will we recognize what we're seeing when the next one arrives? Will we remember what 3I Atlas taught us? To look harder, question deeper, and not cram everything into boxes just because new categories are uncomfortable? Will we have the guts to admit, I don't know when that's the truth, and the curiosity to chase the data wherever it leads, even if it's not where we hoped? That's what science is. At least it should be. Not pretending to have all the answers, but owning up to the mysteries and chasing understanding with everything we've got. Even when it's hard, even when it makes us uneasy, even when the truth turns out to be something that shakes the ground we thought we stood on. 3I Atlas is still out there right now, late December 2025, cruising through the outer solar system at about 12 kilometers per second, heading for interstellar space. The data from its flyby keeps scientists busy. People are still analyzing, still writing papers, still bouncing drafts back and forth with reviewers. The debates haven't let up. You hear them in conference rooms, see them in sprawling email threads, and catch fragments of them echoing through late-night Zoom calls between researchers on different continents. The truth is, nobody cracked the mystery yet. The weird stuff, those anomalies, still don't add up. Amateur astronomers keep posting their images online, fueling arguments and wild guesses. The scientific establishment doesn't officially back these ideas, but it can't really stop the rumors either. There's still a gap between the official line and what the raw data suggests when you look closely. Picture a scientist hunched over a screen glowing with spectroscopic graphs or brightness curves or polarimetric data. They're staring at the numbers and asking themselves, what if we're wrong? What if we started down the wrong path from the beginning and that's why nothing fits? That kind of wondering matters. Doubt is fuel for science. The moment we stop asking questions and get too comfortable with our models, we stop discovering anything new. Whatever 3I Atlas actually is, whatever story it's telling, it's handed us a real gift. It's made us uncertain again. It's forced us to look closer at the sky, to rethink what we think we know, to wonder what else might be slipping past us simply because we're not looking for it or don't recognize it. That's the real lesson here. More important than nailing down the exact composition or origin, or whether this thing is natural or something stranger, the lesson is that the universe still has surprises. We're still taking baby steps in understanding what's out there. Every assumption is just a placeholder, every model just an approximation, and all our neat categories are more for our convenience than any absolute truth. When you hear nothing official, don't mistake it for ignorance. Most scientists working on 3I Atlas are sharp, careful, and know the data inside out. The silence is really just an admission. Sometimes the questions are bigger than the evidence. Jumping to conclusions or making loud claims before the facts are in doesn't help anyone. Patience and rigor matter more than quick headlines. The truth, whatever it is, deserves more than a rushed answer, but silence only works for so long. There comes a point where caution shades into avoidance, and prudence starts to look like inertia. If the gap between what scientists know privately and what they say publicly gets too wide, trust erodes. People outside the system start seeing patterns that insiders either miss or just won't talk about. Honestly, we're probably getting close to that line with 3I Atlas. The weird data keeps piling up. The amateur photos are getting harder to wave away as glitches. Anyone reading both the careful, hedged papers and the upbeat press releases can spot the disconnect. Just a comet is sounding less convincing by the day. Sooner or later, someone's going to have to admit what's on everyone's mind. Maybe 3I Atlas doesn't fit any of our neat categories. Maybe it's not artificial in the way we usually mean, but it isn't exactly natural either. Maybe it's something in between. Or maybe it's something else entirely, something we don't even have words for yet. Maybe that day's almost here. Maybe someone's still watching this thing, and the next set of observations finally gives us the missing clue that ties everything together. Maybe a researcher out there decides that telling the truth matters more than playing it safe, and actually puts out a paper saying what a lot of people are thinking but nobody wants to say out loud. We don't really know what this object is, and the usual explanations are hanging on by so many what-ifs that it's time to seriously consider something else. Or maybe not. Maybe nothing happens. Maybe the silence just drags on. 3I Atlas slips out of sight, out of the headlines, and turns into another footnote in some dusty astronomy journal. All those weird details get tucked away, waiting for some future scientist with better gear, better theories, or just a bit more guts to look at them again. Honestly, the object itself doesn't care. It's already billions of miles out, way past Neptune, drifting through space on a path it'll never return from. The sunlight out there is barely anything, more like a memory of warmth than the real thing. If there was any gas still leaking from the object, it's probably stopped by now. The coma's gone. It's slipping back into hibernation, just like it did for 1,000,000 years before the sun's gravity pulled it close and gave us our one chance to look. Give it a few more years, and even the biggest telescopes won't be able to spot it. In 10 years, it'll be just another faint speck, lost in the sea of distant galaxies and quasars. A few decades from now, it'll pass beyond the heliosphere, the edge of the sun's influence, and slip into true interstellar space. Whatever secrets it holds, whatever answers we missed, those secrets are leaving with it, locked away in ice and rock, out of reach maybe forever. Unless we already have what we need. Maybe the data we've gathered is enough. Maybe, if we're honest about it, the real problem isn't missing information, but what that information actually means. Maybe the evidence already points to something weird, something nobody wants to say out loud because it's too uncomfortable, too disruptive, too strange. That's the question hanging over all of this, isn't it? Not just, what is 3I Atlas? But are we really ready to know? Are we willing to accept that the universe might be way stranger than we've told ourselves? That interstellar space could be busier, wilder, just more alive than we've imagined. That maybe the lines between natural and artificial, expected and unknown, aren't as sharp as we want them to be. Are we ready to follow the data wherever it points, even if it leads us somewhere that shatters our sense of how things work? Even if it means we know less than we thought, or aren't as alone as we imagined? Even if it hints that intelligence, technology, purpose, those things might be out there all over the galaxy, showing up in forms we barely recognize. Science is supposed to be fearless, right? That's the dream. That's why people get into it, to see things as they really are, not just how we wish they'd be or how we're told they should be. But scientists are just people. People are messy. We've got our own blind spots, fears, career worries, all the social stuff that decides what we can say out loud. We want mysteries to have tidy answers, to fit into boxes we already know. We want surprises to turn out to be just old stuff in disguise, maybe with a little twist, but nothing so big we have to throw away the whole rulebook. We push back against big, uncomfortable changes, even when the data says we shouldn't, because facing that means admitting a lot of what we thought we knew was wrong, or at least not the whole story. 3i Atlas doesn't care what we think or want. It just is. And honestly, nobody really knows what to do with it. Every measurement, from pros and amateurs alike, points to something that doesn't sit neatly in any category. It's got a bit of a comet vibe, sure, but in other ways, it's like nothing anyone's ever seen. Maybe it's natural, just not in any way we understand yet. Or maybe it's forcing us to rethink what natural even means in a universe that's way more wild, busy, and strange than the hollow, clockwork cosmos we used to picture. And yet, no one's really talking about the big possibilities. The silence is loud, but it won't last forever. Someone going to break it. Someone will publish, say what the data really shows, and risk their reputation to get it out there, no matter what the institutions want to hear. When that happens, everything shifts. The questions become impossible to dodge. The data starts demanding real answers, not just cautious hedging and statements so careful they end up saying nothing at all. But for now, we're left with scraps, polarimetric curves that don't match anything else, crazy composition ratios even for interstellar stuff, structure that shouldn't hold together but does, activity where there shouldn't be any, features that look too organized for comfort, sizes that somehow stay fuzzy after months of study. Amateurs snapping pictures that catch weird details the big telescopes miss or blur out. And there's this growing feeling, at least among those really paying attention, that something big is getting missed or quietly ignored. Not some conspiracy, just the usual mix of caution, career worries, and the basic human urge not to be spectacularly wrong about something that matters. 3i Atlas is more than just another comet from out there. It's a test. How do we deal with stuff that doesn't fit the script? Can science still follow curiosity and evidence, or is it just about sticking to the old playbook? Are we willing to sit with the weirdness long enough to actually learn something, or do we rush for easy answers to stop the uncomfortable questions? We don't have the results yet. The data keeps trickling in as the thing fades. People are arguing over it in conference rooms and email threads. Everyone's got their own theories, their own axes to grind. But one thing's obvious already. 3i Atlas changed the whole conversation about interstellar visitors. Suddenly, it's not just a thought experiment or a one-off. These things might show up all the time, we just never had the tools to spot them. And it's a reminder, the universe isn't waiting for us to get our act together. It sends whatever it's got, whether we're ready or not, whether we know how to make sense of it or not, whether we like it or not. What we do with that, whether we look at it honestly or toss it aside because it's inconvenient, that's up to us. Time's running out. As of late December 2025, you can still catch 3i Atlas with a big enough telescope, but it's fading fast. In a few months, it'll be too dim for good spectroscopy. Give it a year and you won't get any useful data at all. The chance to solve its mysteries is slipping away, and the big questions stick around. What did we actually see? What does it mean? Why was every measurement a surprise? Why do the standard models need so many tweaks to fit this data? Why won't anyone just come right out and say what they really think, even though we've got better observations of this thing than any other interstellar visitor? And most of all, are we being truly honest about what we know and what we do? We still don't have answers to those questions, not real ones, not ones everyone can point to and say, yeah, that's it. But answers are possible. The data's there. The observations are sitting in archives. The evidence, whatever it turns out to mean, is waiting for anyone willing to look hard enough and be honest about what they see. And the longer we avoid those questions, the more obvious the gap gets. Official statements say one thing, but if you dig into the technical papers or listen to the amateurs, you see a messier reality. The silence starts to feel loud. You can't help but sense that people are leaving something out. It's not because anyone's scheming or trying to hide things. It's just people being people. No one wants to look foolish or admit they don't know. We all like to stick with what feels safe, wait for someone else to go first, pretend the weird stuff isn't there. But someone has to go first. Someone needs to look at 3I Atlas and say, hold on, this doesn't add up. Maybe it's not a normal comet at all. Maybe we seriously need to consider other possibilities. Maybe that's you. Maybe as you read this, you're the one connecting dots that others are trained to ignore. Maybe you decide that asking the hard questions matters more than the risk of looking foolish. Or maybe not. Maybe this thing just gets filed away with all the other oddities, talked about, never explained, left for someone else to figure out later. Either way, the story isn't finished. More interstellar objects will show up. The next one could come next year or in 5 or 50. But it's coming. And when it does, we'll have to decide all over again. Do we look at what's in front of us, or do we keep shoving things into familiar boxes because that's easier? 3I Atlas is teaching us, whether we like it or not, that comfort and truth don't always go together. Sometimes the best discoveries are the ones that make us squirm. The universe isn't built to fit our expectations, and it doesn't wait for us to catch up. The data is weird. The silence says something. The whole thing is unsettling. And somewhere out past Neptune, moving toward the edge of the solar system, there's an object unlike anything we've ever confirmed, holding on to secrets we might never unlock. Unless we decide to be braver, unless we're ready to follow the evidence, even when it drags us into places we never wanted to go. That choice is ours. The universe has put something in front of us. What we do with it, how honestly we face it, that's up to us. 3I Atlas is out there waiting. Or at least the data is, watching to see if we'll really look back and start asking the hard questions. Waiting to see if we can still be surprised, or if we'll just keep bending reality until it fits what we already believe. How we answer says a lot, not just about what 3I Atlas is, but about who we are as explorers. Are we still curious, still humble, still gutsy enough to admit when something doesn't make sense and chase after the truth anyway? That's the real test. And like it or not, we're in the middle of it. Since 3I Atlas first showed up in our telescopes, something changed in the astronomy world. Nothing dramatic or overnight. But if you pay attention, if you listen to how people talk about these interstellar visitors now compared to before, you can feel it. It shows up in conference questions. Before, when someone talked about a far-off comet or asteroid, people stuck to the technical stuff, uncertainties, models, comparisons. The usual. Now more often someone in the crowd asks, have you checked the polarimetry? Does the composition make sense? Any weird shapes? That old automatic assumption, this is just another comet, doesn't hold the same way anymore. You can see it in the grant proposals going to NASA and the National Science Foundation. More scientists are pitching surveys built just to spot and study interstellar objects. More are asking for money to develop analysis tools that don't assume everything out there acts like a typical comet from our own solar system. The whole field is getting ready for more visitors, and this time, ready to treat them as a big deal. You also hear it late at night, when the senior scientists have gone home and the grad students and postdocs are still talking. They wonder what they'd do if another Oumuamua appeared. They debate which measurements would actually tell us something new. They talk about how to design observing programs that could finally clear up the mysteries, instead of just writing down that they exist. Some even wonder if the most exciting work in planetary science is about to shift from our own solar system to the stuff that wanders in from others. And there's this quiet truth that nobody says out loud, but more and more people accept. We're not actually that good at this yet. All our ways of thinking about small space rocks were built on what we know from our solar system. But those ideas might just fall apart when we're dealing with objects that formed somewhere totally different and traveled through places we've never seen and can't recreate. 3I Atlas forced us to admit that. It didn't hand us easy answers. Instead, it showed just how many of our answers rested on assumptions we'd never really questioned. It marked the edge of what we actually know, the place where our models stop working and we start telling ourselves stories, just to make sense of things we don't understand. That's uncomfortable, but it's important. Science doesn't really move forward when everything goes as expected. It moves when something breaks the pattern. 3I Atlas broke the pattern in so many little ways you couldn't just wave it away. Sure, each weird thing could be explained on its own. But when you step back, the pile of oddities points to something bigger. Either this thing is a freak accident, or maybe our expectations were wrong all along. The conservative view says it's just a fluke, a weird comet from a weird system that just happens to be strange in every way. Sure, that's possible, but if your whole answer is, it's just weird, you're not really explaining anything. You're just putting a label on what you don't understand. The more honest answer is just to admit it. We don't know what 3I Atlas is because we don't have enough information. We've seen 3 confirmed interstellar objects, Oumuamua, Borisov, and now this. 3 out of what could be billions drifting through the galaxy. That's nowhere near enough to know what's normal and what's actually odd. Imagine trying to figure out all of Earth's animals after seeing just 3, and one of them is a platypus. Is the platypus a bizarre outlier, or is your idea of normal just too narrow? We need more data. We need to watch more of these visitors, study them carefully, and compare them. We need enough examples to tell the true oddballs from the regular ones. We need to stop being shocked every time something doesn't fit our solar system templates and start building new ones based on what's actually out there. That's finally starting to happen, partly because 3I Atlas left us no choice. The Vera C. Rubin Observatory is about to start scanning the whole sky over and over, and it should find dozens, maybe hundreds of interstellar objects in the coming years. Its main project, the Legacy Survey of Space and Time, will spot them early, while they're still far from the sun, giving scientists time to get organized and watch them up close. There's real momentum for future missions, too. People are drawing up plans for spacecraft that could chase down one of these objects, match its speed, and fly alongside it for months, taking photos and measurements we just can't get from Earth. These missions aren't funded yet, but they're being taken seriously in a way they just weren't before Oumuamua and 3I Atlas showed up. The universe is huge, and honestly, we've barely scratched the surface. Our galaxy alone has hundreds of billions of stars, trillions of planets, and a wild number of smaller things drifting around. Out of all that, we've only poked and prodded a tiny bit, almost all of it right here in our own solar system. Still, we build our theories from this tiny slice, convinced we're onto something big. But then, every so often, something weird shows up from outside our comfort zone. Suddenly, the rules we thought were ironclad don't quite work. That's when we hit a fork in the road. We can either bend our theories out of shape, patch them up with exceptions and hope nobody notices the seams, or we can admit it. Maybe our ideas are too small, shaped by what we've managed to see so far. Maybe we need new ideas, new language, a whole new way of seeing things. It's always easier to stick with what we know. That way, nobody has to admit they're stumped. But taking the other path, admitting I don't know, that's tough. It means stepping out on a limb, risking your reputation, maybe getting it totally wrong in front of everyone. Then along comes 3I Atlas, barreling right into that second path whether we want it or not. This thing refuses to fit our neat little categories. The more we learn about it, the stranger it gets. Eventually, there's just too much oddness to ignore. Maybe we'll reach our breaking point soon. Or maybe it'll take years. after we've seen more interstellar visitors and figured out where 3I Atlas fits. Or maybe we never will, and it just hangs there, forever a question nobody really answers, just a weird blip in the records that everybody moves past. Either way, the question's out there now. It shows up in the data, hidden in the cautious wording of research papers, in the fuzzier images from amateur astronomers, even in the way seasoned scientists hesitate when someone asks them to explain it. What is 3I Atlas really? What does it mean for us, for our understanding of the universe? These are the big questions, and for now, they hang in the air. Not because we're ignoring them, but because the answers are harder to pin down than anyone guessed. The universe, as usual, isn't playing by our rules. And sometimes the most honest thing science can say is this: we don't know yet. We're working on it. We're gathering evidence, thinking it over. But for now, we just don't know. Right now, 3I Atlas is already billions of miles away. Just a fading speck, secrets in tow. But the data's still here with us. The questions haven't gone anywhere. The mystery's alive. Somewhere out there, someone, maybe in a backyard under the stars, maybe in a big lab, maybe on a grad student's laptop at some ungodly hour, is staring at the data, trying to make sense of it, wondering what exactly we saw. Wondering if we'll figure it out before the next strange visitor cruises through and leaves us scratching our heads all over again. The universe keeps tossing us these puzzles. Whether we learn to read them right, whether we realize when we're fooling ourselves, whether we stay humble enough to admit when we're totally lost, that's the real test. 3I Atlas was one of those puzzles. There will be others. Each time we have to ask, are we really seeing what's there or just what we expect to see? That question matters. If we let our old ideas blind us, we'll keep missing out. We'll keep hammering square pegs into round holes and congratulating ourselves when they mostly fit, never stopping to wonder if we're using the wrong game pieces altogether. That's what 3I Atlas leaves us with, not an answer, but a challenge. Not a tidy conclusion, but a reminder to think harder about what it really means to understand something. It's an open invitation to wonder what else is slipping through our cosmic backyard right now. Things we miss because we're not searching. Things we don't recognize because they don't fit our boxes. Things we just don't see because we've decided everything that matters is already labeled and logged. The universe is weirder than we think. 3I Atlas proves it, no matter what else you say about it. And that weirdness isn't packing up just because it makes us uneasy. It's right there, in the numbers in the telescope feeds, in those cautious lines scientists slip into their papers, and in their exasperation when the models keep breaking unless they toss in another "what if?" It's there, and it keeps waiting for us to actually look, really look, without all the blinders and safety nets that help us pretend we've got things figured out. So here's the real question: are we ready to face it?